Assalamualaikum. We are from Group D. We are going to present about N1, which is Rutherford scattering cross-section measurement. First of all, let me introduce our group members. First, I am Aina Mazliana with my friend, which is Aisha and also Aisha Dalila. Let's start with the abstract. So, Rutherford scattering purposely to examine the structure of atom. So, in this experiment, we are trying to investigate the differential cross-section of alpha particles scattered by a thin gold foil. Thus, verifying the prediction of Rutherford scattering, we measured the count rate of the scattered particle at various angles, which is between -30 to +30 degree. We used different thickness of the gold foil to see the distribution of the deflected particles and the particles that are not deflected. For those particles that are not deflected, we assume that the alpha particle does not collide with the atom in the gold foil. The objective of this experiment is to record the direct counting rate of a particle scattered by a gold foil as a function of angle theta. Next, to determine the corrected counting rate n with respect to the scattering distribution in space. Third, to validate the Rutherford scattering formula.
Next, let us move to the introduction based on Rutherford scattering. Understanding the structure of the atom has always been important in physics. Over time, scientists like J.J. Thomson, Ernest Rutherford, and Robert Millikan each made discoveries that helped shape the atomic model we use today. In 1897, J.J. Thomson discovered the electron using a cathode ray tube. He introduced the plum pudding model, which imagined electron floating inside a positively charged soup. But this model couldn't explain how positive charge was really arranged in the atom. Later, in 1909, Ernest Rutherford performed his famous gold foil experiment. He shot alpha particles at a thin sheet of gold and noticed something unexpected. While most passed straight through, some deflected and a few bounced back. This led him to suggest that the atom has a small, dense, positively charged nucleus and most of the atom is just empty space. Not long after, Robert Millikan measured the charge of the electron using the oil drop experiment. His work proved that electric charge is quantized, which helps strengthen our understanding of subatomic particles. In our experiment, we aim to test Rutherford's conclusion. We used a radioactive alpha source and gold foil to measure how alpha particles scatter at different angles. Then, we compared our result with the theoretical Rutherford formula, written as 1 over sine to the power of 4 theta over 2.
Let's move to the next part, which is our literature review of the experiment. The Rutherford scattering experiment, also known as the Giga-Marsden experiment, involved bombarding a thin gold foil with alpha particles to investigate the structure of the atom. The results of this experiment led to the development of the nuclear model of the atom, suggesting that atoms have a small, dense, positively charged nucleus surrounded by negatively charged electrons. For the formula is d sigma over d omega is equal to 1 over 4 pi emissivity multiplied by Z1, Z2, e to the power of 2 over 4e in brackets to the power of 2 multiplied by 1 over sine to the power of 4 theta over 2. For the n theory is equal to k over sine to the power of 4 theta over 2. Here we can see that the Z1 is 2 alpha particles and Z2 is 79, which is gold. For E, 5.486 exponent 6 electron volt is equal to 8 to the 8.79 exponent -13 joule. For not is 8. For the emissivity, 8.854 exponent -12 F over M, and R 0.05 M, and N is the number of atoms per meter squared based on foil thickness. Here we can see that the Thomson model and Rutherford model, we can say that there is a difference between these two models. For the left, which is a Thomson's model, has been correct. All the alpha particles should have passed through the foil with minimal scattering, as we can see here. And for the right is what Giga and Marsden observed was that a small fraction of the alpha particles experienced strong deflection. And we can see the observed result from this example.
Next, let's move on to the methodology. So the apparatus that we use is scattering chamber, gold foil, vacuum pump, power supply detector, collimator slit, and radioactive source. For the procedure, we're preparing the chamber by putting the gold foil and clip with the slit. Next, radioactive source was inserted into the chamber and detector was fixed on the BNC. The chamber was closed. Then, the vacuum pump was switched on to pump the air out of the chamber. Then, the angle was set to 0 degrees. The electrical counting was switched on and then the time was set to 100 seconds. The start button was pressed. Once it reached 100 seconds, stop button was pressed and the data of impulse rate was taken. The data was tabulated and the counting rate is measured. Step 6 until 10 repeated using the different angle and time is shown in the result. Here is our experiment setup.
Next, let us move to the result. Here, we see the result for gold foil sample C. The pulse count from the 3 readings were averaged and then corrected for space and geometry to get the final counting rate N in counts per second. The corrected value for sample C peaked at around 34.42 count per second. This table shows the same analysis for gold foil sample K, which had a slightly thicker foil. Again, we took 3 readings at different angles and corrected the raw pulse count. The highest corrected rate reached 59.38 counted per second, which is higher than sample C due to the possible differences in foil thickness or scattering condition. This is the plot of sample C's space-corrected counting rate versus scattering angle. As expected, we see that the count rate is highest at a small angles and decreases sharply as the angle increases, which support Rutherford's scattering prediction. Similarly to this graph shows sample K space-corrected data. Despite the noisy data and negative values due to the correction, the overall trend is still sharp decline with increasing angle, consistent with the scattering model. Here, we use Rutherford formula to calculate the theoretical scattering rate. The key parameters are Z1 equal to 2 for alpha particle, Z2 equal to 79 for gold, E energy equal to 5.486 MeV, distance R equal to 5 cm. We use this to calculate the constant K and the model n theta using K over sine to the power of 4 theta over 2. This table compares the theoretical and experimental N values for both sample C and K. The experimental counts are far lower than the theoretical ones, which is expected due to the equipment sensitivity and simplified assumption. This graph shows the Rutherford scattering fit to sample C's data. After 2 iterations of fitting, the model converged. The fit curve closely follows the experimental data trend, validating the inverse sine to the power of 4 relationship. And here is the fit for sample K. Similar steps were followed, and the fit also shows a similar trend with a sharper drop-off at a larger angles. Again, the root mean square residual and variance confirm that the fit was statistically consistent. Here, we calculated the percentage error using the formula percentage error equal to experimental minus theory over theory times 100%. In some cases, the error reached up to 100%, especially at small angle. For analysis, both samples showed peak scattering at small angle, matching Rutherford's prediction. Sample K had a higher count rate due to its foil characteristic. The data followed the theoretical curve even with high percentage errors due to equipment limit and scattering effects. This experiment successfully demonstrated the scattering trend predicted by Rutherford's atomic model.
For the discussion, this experiment is to determine the direct counting rate of particles scattered by a gold foil as a function of angle theta. Besides, to know the correct counting rate N with respect to the scattering distribution in space and validate the Rutherford scattering formula. Materials used in experiment, which is thin gold foil that is too thick to detect the alpha particles that can pass through. For the thickness that we use is we have two, sample C and sample K, somewhere around 1.55 milligram over centimeter square and 1.62 milligram over centimeter square. The results shows both sample C and sample K exhibit a peak at 5 degrees. The sample C showing a maximum space-corrected counting rate of N is equal to 34.42 counts per second, and sample K showing a peak at N equal to 59.38 counts per second. Thin gold foil are used because gold is highly malleable, allowing it to be hammered into a very thin sheet. This thinness was crucial because it minimized the number of atoms and alpha particles would encounter as it passed through, leading to more accurate scattering observations. There is a human error when we recording the counted pulse while using the timer, and the percentage error was estimated 100%. From this experiment, we can get a conclusion, which is a Rutherford scattering cross-section experiment, also known as the gold foil experiment, involved firing alpha particles at a thin gold foil to investigate the structure of the atom. It was conducted at the lab with detectors and vacuum chamber with radioactive sources with a piece of thin gold foil and slate. and the result shows both sample C and sample K exhibit a peak at 5 degree. Sample C showing a maximum space corrected counting rate of n is equal to 34.42 counts per second, and sample K showing a peak at n is equal to 59.38 counts per second. The fitted curve closely matched the experimental data points for both sample C and sample K, further confirming that the Rutherford scattering formula accurately describes the scattering behavior observed in the experiment. The experiment did achieve the objective given. We can validate the correct count rate and use the theory of Rutherford scattering formula.